My name is Andrei Kish, I'm from Think, and today I'm going to quickly show you our infrastructure that we're using for doing remote computations. And hopefully we get to run it on a few more images. So let's start with a demo. So one first use case that we're using this is for running tests and examples. So this is first my local GT image, and I'm looking at one package, in this case, brick editor examples, and I can see the examples that I have within this image. And now I would like to run them. Let's make sure they all pass. The way I could do it directly from this view. We can go here, I see I have 834, and let's just click run. We'll wait for a minute or so, or 30 seconds. It takes like this to run them sequentially. Sometimes it's less, sometimes it's a lot more. I played a bit more with this image, so I guess here it will be a bit slower, because yeah, I have a lot of objects. But still, make some progress. But yeah, if I were to do this several times, I will wait a bit of time. Come on, don't slow down the presentation, 200, so yeah. It's making progress, so we will, sorry? Yeah, I did not prepare a joke, so should have been some knock-knock joke, but almost. Okay, we passed half the time. It's a bit slower than usual now, for some reason, because of the demo, I guess. Usually it's 40 seconds, around that. Or time passes slower now that I'm presenting. Maybe that's the reason. Or maybe I have no power, who knows? The laptop might decide. Okay, we are approaching. And now, maybe, okay, finally, come on. Okay, so running in image tests can take some time, and ideally we'd like to not waste the time always waiting. It's done. Now what we can do, for example, I could go here, say I want remote, and run. But before, let me just show you what is going to happen in the background. I'm going to inspect the default instance of the remote runner. So this is the tool that manages instances. It has no workers. So I'm going to start it now. Now, it should say, now depending on how much free memory I have on the machine, it's going to start some background images. Replay all the changes I did in this image since I started it. And then the images are there waiting headless. If I look at the activity monitor, I have now 6 headless images that are here. And now, theoretically, I could run the examples again. Should be 10 seconds around. So now the tests and examples are distributed to those machines, and now I'm done. However, this is nice, but then I'm often starting to develop. And in this case, there is a code sync between this local image and the workers. So every change I'm doing in this image is automatically propagated to workers. Just as an example, let's fail this assertion, and I'm going to save. Now the change has been sent to the workers. So now if I run again all tests remotely, this will fail immediately because it had the change, and now it's replaying, running the test to this assertion failed. So this is kind of a small demo of how we can use this to run tests when we are developing in our local images. If tests or examples take a bit longer, so we can parallelize this. And just as a quick overview of the infrastructure, we have a runner, and this runner we say creates jobs. So jobs is a computation, and the computation we split it into tasks. For example, a task can be run a test or run a group of tests. And then we send this to workers, and the workers can be in image. In this case, we show them a local machine, but they also can be in IWS or other places. And to show something more interesting, I'm going to show you a use case, but of course, I have to log into a remote machine for this, and it's going to ask me for some code. I did it before, but of course, it expired. Okay, so now I logged into a remote machine, and this is a GT image used at Lifeware. Lifeware is a company that manages policies for life insurance companies. And they happen to have a lot of tests. So I think their image has around 35 million lines of code, so 2.5 million methods, and around 150,000 tests. And ideally, they would like to run these tests every time before deploy or committing to make sure that they don't break things. And in this image, they had, I said, 152,000 tests. And if I were to run them sequentially, it takes 9 days and 7 hours. So that's a bit of a longer time. I already did here a run. We will do a live run at the end. In this case, this run sequentially took 16 minutes. It used around 1,000 workers. And I don't like, there are 2 issues in this one. So we're going to see a bit how we could investigate these issues. So first, 16 minutes is a bit too long. I was expecting 12 minutes. So why did it take 16? We're going to try to see. And then, yeah, I did some strange thing because I have 556 failures. I was not expecting this. So let's just see first how will we approach this, looking at these failures. So we could click, and then let's collapse this for the moment, and now we get all our failed tests. Okay, let's look at one test. And we get a stack trace. So the cluster has been terminated, but we brought back from the cluster an actual stack trace. We can see that it's a comparison failure. So most likely 2 things were compared. But now my first question is, what were those things? Luckily, whenever we have a comparison failure, we are also bringing back the 2 things that were compared, the expected and the obtained value. And in this case, they happen to be PDFs. So the way this assertion works is that it generates a PDF, and it compares that it's equal to an expected PDF, just to make sure it's the same. And in this case, we got 2 PDFs, and they do not match. And in this case, we highlight the difference. So in this case, I changed the signature. So a lot of insurance companies, the CEO changes, so then the signature of the CEO changes on all documents. And that's a very common change. We could look at also more things. For example, if I inspect the data from the cluster, we could look at, for example, all the individual differences. So how this comparison is done is that the image is split in 10 by 10 pixels squares, and each square is compared. And then I could see exactly the pixels or the squares that were different between this, if that's what I'm interested in. And in this case, if this is what I want to, if I say this is correct, I could accept this. And now this becomes my new expected value, and the test is green. I will not have to rerun it because this was the only failing assertion in this test. So I can accept it. But now should I do the same for the rest 400? That is going to be painful. So another way to do this is to group all this. So we have all the failures, we have all the documents, we have all the differences. So we can actually group tests together by how they failed. So in this case, I would inspect, and I get an object with all the results. And I can see, for example, that in this case, 31 tests had exactly the same difference here. And this is the list. And they are different documents, but in all documents, there was exactly the same difference. And now I could say, if I select the root, I could say I want to accept all similar changes, just accept everything. So then, instead of going to 400, maybe I will just go to, I don't know, 50 assertions and make sure it's expected and accept everything. And in some cases, you can get really, I don't know, 5,000 documents that fail. And then you just have to go through a few and accept instead of spending hours. And also, I don't have to rerun anything. All the information was brought from the cluster in one run. I can look, accept, and move on. And then at the end, I can rerun one more to make sure everything is green. But you don't have to rerun every time in order to get the data you want. So this is how we will deal, for example, with the failures. But now let's also look at the execution. So we said it takes 16 minutes, but I was expecting 12 minutes. So let's investigate the cluster execution. So we also bring back some statistics when we are running on the cluster. We can access them here. First, they are just these are RWS machines. There are just some statistics about the machines. And then we have here a timeline. So this timeline is going to show 1 line per each worker. So each GT image that run is 1 line. They're around 1,000. And the gray part is the duration. And what is this? So I see most of them finish exactly the same, and there is one that took 5 minutes more. We could use another view, for example, and here we show per machine. So we group all workers per machine, and we can see that we have here 1 machine. That seems, so yeah, we can inspect it. Yeah, we get some details about the workers, but we also get a view that is showing per worker the actual tasks that were executed. And red, we color them if we want to compact as much as possible, and if, like you see here, there was a short task and then a long task. So every time we execute a long task, before a short task, we highlight it. Ideally, we want to execute all the long ones at the beginning, and at the end, just have smaller ones. So we could select, for example, the machine here. And then, we can go to this view, maybe. Or I want this one. And then we can see all the tasks, and at the end, okay, this was my task that did 4 examples, and here there is one example that took 5 minutes. We can select it, and then we see some details about the execution, but then we can also look at the actual test case, the source code of the test. And in this case, I cheated a bit. I put it a 5 minutes wait. But then I could remove it, I could save it, and yes, I could rerun the test right here. I will not have to go anywhere else. And hopefully, yeah, it's 4.4 seconds, so much better than before. So here we went to a workflow where we started from the cluster overview, we dived into a machine, we dived into what happened on that machine, then what was being executed by a worker on that machine, and then looked at the actual source code of the test that was problematic. So in the workflow, we're using the same workflow to do different tools as we fit, or as we need to solve problems. Running tests is one use case. Let's also look at another one that's not necessarily just about testing. Another use case that they have at Lifeware is translations. So they have client applications that are used that use different languages, for example. And in this case, how they do translations, just to show you, they have a translation class, and then in code there are things like this. So the translations that are in the code. So there will be a translation new, and then different languages that are supported. We could also collapse it if we don't want to see the details. It can also be done by default. So you just see the latest, and then if you're interested, then you can go and expand and see more things. And the use case here is that for the admin interface of one of their applications, they needed to add another language. We'll say Polish for this demo. And then the task is find all the strings that need to be translated. And okay, we can do some static analysis, but was a bit harder because they really wanted to translate just that portion of the admin interface. Just a portion of the admin interface is an application, not everything, because yeah, maybe it takes too much. So just find the strings that are really used in the admin interface. So one way that they did it, they spent a few days and they had a small tool that was running, for example, could run a test. It was instrumenting first whenever a translation was created. That was easy, just instrument translation new. And then look at the stack trace, and they could figure out based on the stack trace if that translation was created in the admin interface. So you just see, I'm creating an interface, and at runtime you have all the information. You will know this was being created in the admin interface. I have to translate this. And here I will just run the tool on a single test, and then the result is more or less the list of translations, and I could select one translation. And I see the place in the code. And in this case, I want to add Polish, so there is a button that says translate. So then I get back a refactoring, a transformation that offers me to add Polish, and it translates to Polish by doing a request to Google Translate. So now in the same workflow, I could just apply this change when I translated this part of the string. But now, yeah, doing this for all tests is a bit longer. So here, what we did is we have the infrastructure, the remote runner, and the remote runner is pretty generic. Has a job, has a list of tasks. What it executes as tasks doesn't matter. Can be test cases, but in this case, we are actually executing this collector. So we are able to run all tests and collect all translations from the admin interface. I already run it, but if you look at the job, for example, what did I do wrong? Okay, I did something wrong. Unfortunately, I don't know what. I was expecting something different, but doesn't matter. Yeah, I should have done it locally. Yeah, doesn't matter. So this was the job. It took around 5 minutes to execute, but sequentially, it would have taken around a day. And then the result was this. Okay, okay, sad. Luckily, I have another image here with the same demo. Let me increase the zoom. What do I need to do that? Scale the UI. I forgot the name of the page. Yes. And let's hope it works here. It's exactly the same demo. Yes, perfect, works here. So the other one, I broke something. So this was the job. It took sequentially 4 minutes, and then it would have been executed. It took parallel 4 minutes, sequentially would have taken 1 day and 6 hours. And then at the end, we could, for example, say, give us back all translations that were collected by this. And I should have executed the one below, but that's fine. Now it goes and tries to collect everything. For example, we got 2,571 translations. We could group them by method. I don't know, we could go to a method and see, for example, all the translations it did. And then we can also have a button to say, please try to translate me all these strings. But of course, something is wrong. I don't know what. Let's use this one. And now we were doing a request, and now we get back a refactoring, and now we could see, yeah, we could just translate all these strings like this. And then we could apply this on all 2,000, and then we are done. And now, as the last part, let's try to do a live run. So let's see how that will look like. So I have here a test tool, and I'm going to configure this test tool to, for example, there are different ways, but I would like to replay changes. So I like to take my changes here and put them on the cluster. And I will use, in this case, RabbitMQ. So let's see if this is going to work. So I could start the runner. So we have a controller. So we have a controller that we start that manages communication with workers. In this case, it can be also using sockets or using RabbitMQ. Now the controller is started. And now I can say, please run me all these tests. So now lots of things are going to happen. It's collecting, maybe we can see in the activity log. It finds the list of tests to run. It's going to generate the job to send to the cluster. It's going to collect all changes that I have locally. It will send those changes to copy to S3 somewhere. Each worker then is going to ask the cluster to start. It's starting the cluster as early as it can. Then workers are starting, downloading changes, and then replaying these changes. So let's see. And then it will update here a bit the status of what it's doing. In this case, I asked for 3,500 processors. So I said I want to have 3,500 GT images running in parallel. So this is using auto-scaling groups in AWS, and it will vary. Sometimes you get what you ask for, other times you don't. It is a very dynamic environment. We notice here I also have on-machine workers, so we can also start workers on the local machine if it has enough memory. So in this case, 2 workers are local and they already start executing tests. But from AWS, it's still no answer. Okay, now AWS says you have 3,152 cores running. So processors running. Now it still takes a while for the machine to start, the image to be downloaded to the machine, changes to be replayed, connect to the RabbitMQ server, or notify my local image. It's around a minute or so. And after that, we should see that we have registered workers. Yeah, so now we're just more or less waiting. If you have more powerful machines and you have more workers locally, you can see quite a lot of progress fast. So you don't have to wait till everything is running on the cluster. We are still waiting. Okay, we have finally, they are starting to come. Okay, now see, we have 4,300 running. It's generous, Amazon is generous. Also, this is very dynamic, so the auto-scaling group in AWS can at any time take away a machine. So you have a test running, the machine just disappears. So there is also a retry mechanism in place that detects there is a heartbeat that always pings workers, make sure they're alive. If not, it reschedules. It has to do a lot of stuff because machines are not permanent. They can go away at any time. Okay, 1,400, and it started executing. When we schedule, we always schedule the very long test at the beginning. So, and then, usually at the beginning it takes a while, maybe because if a test takes a minute or so, it's always put at the beginning. So we have 31, 32. Let's just wait maybe till it's at 50 or some percentage, because otherwise, we don't want to just look at it. Okay, we have 2,600. So in this case, we are using ARM workers. So we can add ARM or Intel. And there is an explanation for these numbers. ARM machines usually have more cores than Intel machines. but less memory. So sometimes we cannot really use all cores that we get because the machines doesn't have enough memory to start enough GT images in parallel. So we're always getting more cores that we cannot yet utilize. Okay, 2,800 running in parallel. So it's going well. We're still. So now it should, okay, 3,000 almost. Okay, now we have 5,000. So Amazon is really generous today. And at any time, if we want to see what's happening on the cluster, we could also have a button to see there's the cluster state. And maybe just one interesting thing is the activity. So here we can see how Amazon is giving and taking machines. And just as a side note, for example, it already killed 3 machines. It's launching, terminating, launching, terminating. It's very chaotic. Sometimes it's just coming, going, coming, going, coming, going. But with this, we can kind of see, and also the reason. So if you look at terminating, it will say, in response to an instance rebalance recommendation, whatever. So somebody decided it's time to do a rebalancing, and it got the machine. OK, we have 3,000 now running in parallel, and it's at 3%, 4%. So now here it will start to go faster. We can also inspect the runner. And the runner is a RabbitMQ. So we can look a bit. We have different queues for different purposes, but we can look a bit at what is it doing. So it still has 52,000 tasks that need to be processed. And then, yeah, we can look at the results. We have a few queues that we use. One is for sending tasks, for gathering results, or for the controller. So that's also useful when we want to know what is happening. OK, 3,400 images running in parallel, 7%. It will take around 8 minutes in total until this is finished. And this is quite reliable. I think it's used at Lifeware. In their current process, they are running their whole tests whenever they merge a set of commits. They don't use Git, but it's the same, and it's between 50 and 100 times per day. So it's quite intensive, and everything is fully automated. OK, we still get some failed tests, but some are random. There are still these random tests. And OK, and this will continue. We have 3,400, and we are at 13%. Let's just wait till it's, I don't know, 20%, and then, yeah, it just goes on. If we have too many reds, for example, we could always stop the execution and not let resources being wasted. And like this, yeah, they are able to run this 9 or 10 days of computation within 10, 15 minutes. Yes? How much does one of these runs cost? I don't want to know the answer. Maybe you can ask somebody from Lifeware, but I'm doing several per day, so I'm contributing to giving AWS income. So now we have 5,500 cores running. Just maybe quickly, we can just check the cluster. Let's see how many machines do we have. I have 95 machines now running, and then they are of different sizes. Just to quickly check, maybe this is what I want. So yeah, some machines have 96 cores, 192 cores, and 700 gigabytes of RAM. So some machines have terabytes of RAM, so it's varied. This is a big one, 192 and 1.4 terabytes of RAM. So it varies. It varies a lot in terms of processors, machine cores. It's a very dynamic environment. We are trying to get as many machines as possible, because then the chance that we get machines fast is bigger. OK, so it's 74%. Actually, I've been OK. OK, well, it will also, let's wait till it's finished. There will be a small cavity here, because this runner, the one with the message queues, is a bit new. So if things fail, it reschedules them at the end. And yeah, it's a bit, so usually the last ones are going to take a bit longer, but we don't have to wait. So 90% when we started at 46, and now it's 53. So around 7-8 minutes will be in total, and 3,700 workers. Most I did, but not for tests, for other tasks, was 7,000 workers. That was the maximum we could. But we didn't need more. Maybe we could go more, but at that time, we stopped there. And yeah, now he's going to take a bit more time here, because he's going to retry. So we see that it retries 740 tasks. And this usually may be tests that need to be retried because the machine disappeared. But this is usually a bit long, because we need to reschedule them and really run them immediately, not reschedule them at the end. So they should be with a high priority in the queue. Okay, so this was what I wanted to show you for the demo. So it works to run things in parallel at more or less any scale you want and go to a few thousand parallel images doing any computation that we want, given that we can get enough machines to do the, okay, it finished, took 8 minutes. So much better. And to end, what we looked at were a few different use cases. So we tried to look at, we saw the PDF differences, so examining why the assertion failed. Then we were looking at, the cluster. We looked a bit at why the execution took time. I forgot to look at something, doesn't matter. We look at the translation part where we were accepting translations. And in this case, we all did this in the inspector. We never used a different tool. And if we look at one, what we see that the inspector, we have a flow. And in the flow, we can have views and snippets. And we can combine them in any way that we want in order to answer questions. And the way we think about this in GT is that we like to think of the user interface as a language that has very visual operators, a view, a snippet, an action, and that are put in a flow, and then the users are the ones that are free to combine these operators in order to solve various problems that they have. They don't have to go to a special tool. They can, there in place, build the flows that they need to solve whatever problem they are encountering. Okay, so that's what I wanted to show you today.
Thank you very much.
Welcome.
Thank you, Andre, for your presentation. Is there any questions before?
Hi, Andre. It looked like there at some point were almost like 6,000 reservations or machines available, nodes available, but it only went up to like short of 4,000 actually using it. Can you explain what the reason is why not more?
Yes, like I said, it's
used?
the ARM. So initially we use Intel machines. Intel machines are more expensive than ARM machines, but are beefier somehow in AWS. ARM machines have more cores, but less memory. So sometimes if you get a machine with 192 cores, but little memory, we cannot start 192 GT images in parallel because there is not enough memory. So we just start 100 maybe, because we can start 100 safely. So then 92 cores remain unused. So that's why for ARM, for Intel, we're getting exactly the same numbers because Intel machines had less cores and more memory. Have more cores, ARM is more cores and less memory from what we are seeing. Welcome.
Yeah, I agree. Very, very impressive. One question. I don't know the GTVM or FAROVM, but it's common that upon image startup, the virtual machine allocates some kind of memory related or depending on the size of the image. So I wonder, when you deploy these thousands of cheated images, are these development images that may take, 40, 60, whatever megabytes, or do you prepare special headless, tiny images with a remote runner only?
No, they are normal development images. So we allocate 5 gigabytes per image. That's our current. So we want them to be the same as the image you have locally. So usually you have a base image locally. You download a LiveWare image that has a number. And then on the cluster will download exactly the same image. Same state, same everything. Otherwise, you always get differences. So we still need to reduce a bit the size of the image, but we don't lose much. So maybe if we're at 4 or 3 gigabytes, we'll be fine, but currently. And of course, if you need more data, maybe you need to run more, then we increase the size. But currently, it's 5 gigabytes per image.
Thank you very much for this interesting talk. Can you give us some information about your cloud cost?
No, that's LiveWare specific, I do not. But I can tell you that the ARM is cheaper than Intel. That's the only.
The development image you started everything from, this is the central coordinator also. Then everything is reported back to this one,
Yes.
or is that you can only see the results on this machine also. So, or is it another coordinator, central coordinator, or something in between?
Yes, good question. So you see here runner. So this has different options. So we can choose where this coordinator is. In this case, it's in this image. In its messages queue, we can want to say start another headless image, and that coordinates everything. Because sometimes if you still want to work in this image while things are happening, it will be slow because it needs to get data. So it's okay, spawn me a headless image, that handles everything, and just get the result when you're done. We had before when we were putting this image on another server, but we didn't gain much from that, so we removed that. So now it's either your local image or a headless image that's on your local machine.
Yeah, and can you, can you connect from another image to this coordinator? So let's see, if you start remote and then your machine crashes. So what happens with all the runnies? Can you reconnect to this coordinator?
Right now, no. So right now, if it's dead, it's dead. You have to stop the cluster more. The cluster has a 20 minutes timeout because otherwise it cannot go more than 20 minutes, then it's dead. So.
Thank you very much. Now we are going to have the next presentation.
Thank you.
GeoView.